So that's for the most part, right? How you get contraction, right? How you get that, how you develop force, right? Your starting length of your sarcomere and hence the starting length of your muscle, right? The frequency of stimulation. The more you stimulate, and the faster, the higher the frequency, that is the faster the stimulations come, the greater the contraction you can come. Okay, and then the more fibers that are contracting, obviously, the more force you're going to get in the entire muscle. So the last thing I want to mention here are these terms isotonic and isometric over here, and these contractions, because you'll see those. And what you want to remember about these is tonic means the tension, and iso means same, right? So same tension. And if iso also means same over here, what's metric mean? Size, right? This is the easiest way to think of these two. Isotonic or isometric. In both cases, we're talking about contractions. At one time, right, the tension is going to remain constant, right? You're going to put a certain amount of innervation into it, and the muscle is going to change its length. In this case, it's going to shorten and move a load. Over here, this is a concentric contraction in particular. So this is going to, the force, the stimulation is going to cause the muscle to shorten, and because the load is, it's enough to move that load over there. And it's called an isotonic, right? It would be the same amount of stimulation, but your muscle is changing. In this case, it's shortening. Because as we'll see, there's two types of isotonic contraction. Right? So that is moving, and this is what you're normally kind of thinking of when you're thinking of muscle contraction, right? That's because that's the whole point of contraction, right? You're moving stuff. But there's also isometric, whereas the stimulation is occurring, the muscle's contracting, but you wouldn't know it really, not too much from the outside. You could feel it, right? You could do this yourself right now. You could put your arm under the, you put your hand on the table, try to lift up the table, right? You're probably not going to lift up the table, but you know, if it doesn't move, your muscle is still contracting. You're creating a force, but you're not, it's not enough to move that object right there. So there's contraction, but there's actually no lengthening of it. And we'll look at why that happens. Again, I don't know if your book goes into it too much, but in general, right, when you're looking at that isotonic contraction, moving a muscle, again, this is a so-called concentric contraction where the muscle is shortening, the muscle is stimulated, and that force that was generated, right, was the force that was generated is enough to move the load over there, right? You're contracting enough muscles to move that 20 kgs. Whereas in an isometric contraction, you're generating a force, but, right, not quite, right? 30's up here, you haven't reached that yet, right? So the muscle's generating, muscle is contracting, it's generating force, but it's not quite enough, right? In this isometric. And because the total length of the muscle isn't changing. So this again is not in your book, but I want to explain it because it's, you know, a little bit of a hard concept. You know, when we talked about the organization of the muscle fibers, right? We said that there was connected by the endomysium and the perimysium and the epimysium, right? Those connective tissue layers. And I told you that they were part of the elastic elements, right? Because the force that was generated, I was going to like work through these connective tissue layers ultimately to pull on the bones right there. They were all worked in series over here with the contractile forces. Right? But there was also within them a little bit of stretchiness. They had a lot of elastic fibers, right? Not just collagen fibers. There was elastic fibers within them, right, that we're going to be able to stretch. There was also, remember, this is the actin filament. This is the Z disc over here. This is the myosin filament. And I said, this accounts for your sliding filament theory. They didn't even discover this protein over here, for like 20 years ago. It's the biggest protein that's ever been found, right? That's why they called it Titan. Titan, right? And it's connecting the myosin filament over here, and it's intertwined with your actin filaments and ultimately connected to the Z disc. So when this is moving against each other, right, you're actually creating a stretch of the Titan, right? And that's going to kind of creating a little bit of a tension here. Right? Either way, it's more complicated than this, right? Because it's also doing things when it's contracting as well. But this element right here is part of the internal sort of elastic elements of muscle. And that's going to be part of what is maintaining the this isometric contraction, right? You notice this is the muscle length. Here's the sarcomeres. You can see the sarcomeres are contracting, generating forces, right? But the elastic elements within them, and that's going to include not only the titin, but the connective tissue elements within them, they're being stretched a little bit. So your entire muscle isn't being stretched, but because the internal sort of elastic ones are being stretched, even while you're generating force. Once the force that you're generating is enough to overcome whatever load you're doing right there, those, right, the elastic elements already stretched and the muscle allowed to be shortened, right? So when we talk about isometric contractions, if you start thinking about it a lot, it gets confusing. And this is the reason you can actually do that, generating force while not actually. So that was isometric versus isotonic. For isotonic contractions, I also want to mention these two terms right here, right? Concentric versus eccentric contraction. And it's another sort of confused in the literature, and really they don't really understand it completely, but I'll just describe it as best I can right here. So you understand the basics of it and what they mean, what the basic two terms mean right here. There's going to be two types of these isotonic. That is, the muscle length is changing right here. Right? Isotonic, the muscle remains almost constant while the force developed remains constant while the muscle changes in length. Right, and I was mentioned it changed in length, and the examples I was showing was that the muscle was shortening and was pulling on the structure. That type of isotonic contraction is called the concentric, right? It's the normal one thing you're thinking of when I say the biceps brachii. Its action is to flex at the elbow, right? That's a concentric isotonic contraction right there. That's kind of what we're thinking right there. So the tension generated great enough to overcome the resistance. The muscle shortening pulls on the other structures. Those two bones are going to be pulled around the fulcrum, right, toward each other. Right, but on the other side, what's on the other side of the biceps brachii, right? We have the triceps brachii. And I said that there was an agonist and an antagonist, right? When one muscle is contracting, another muscle is being stretched, right? So this gets us into this other one. And it's really kind of a little bit confusing, or, the terminology between stretching and eccentric contraction is not very clear, right? So when you're stretching your muscle, it's not completely flaccid, right? It's not complete, it doesn't have no force generated. So they consider this an eccentric contraction. Right? You need to control that lengthening of the muscle so it doesn't overstretch, right? So you need a little bit of a braking mechanism. So as you lower that object, in this case, the book right here, the bicep is lengthening, right? As your triceps are contracting, they're going to lengthen in a controlled manner. They're not just going to go completely limp from contracted to completely relaxed, right? It's going to still kind of hold on to those. The myosin heads are still going to maintain some grip on the actin filaments. And so there's still some contraction going on, even as the length of a muscle is increasing. But that's the bottom line right here. Muscle shortens and pulls in a concentric. And in an eccentric, the length of a muscle is increasing even though there's a contraction going on. Right? It's not enough to overcome the load, right? Just kind of strong enough to do it, allow a more smooth movement, right, based on the length of that muscle. So that is concentric and eccentric isotonic contraction. These are some of the words that we might go. And again, the difference between eccentric contraction and stretching, it's not really too clear in the literature what the difference is, if any. Okay, so these are the two terms. And another thing is that eccentric contraction is really actually hard to explain from the sliding filament theory. So don't think about it and don't ask me about it, because our brains will simultaneously explode. So that will do it for this little lecture portion of it. All these, the control of the muscle tension over here. Last time, again, we started with the initial length, the higher frequency of stimulation, and the number of motor units. Now you understand what that is, activated at any given point. And that's going to contribute to the contractile force. And then along the way, we talked about muscle tone and how it's maintained and everything. So, and then next time, we'll get into muscle fiber types, fast and slow twitch, as well as the metabolism of the muscle, right, which will be involved in that type